This is the 6th day of Advent of Cyber 2023, and this challenge is called Memories of Christmas Past. Throughout the merger, we have detected some worrying coding practices from the South Pole elves. To ensure their code is up to standards, some frostlings from the South Pole will undergo a quick training session about memory corruption vulnerabilities, all courtesy of the B team. Welcome to the training. So the learning objectives for this is to understand how specific languages may not handle memory safely, understand how variables might overflow into adjacent memory and corrupt it, and exploit a simple buffer overflow to directly change memory you're not supposed to have access to. So for this challenge, we need to start the VM, which you do up there, and there is a direct link to it. So you start it up, and then when it's still start up, there will be the link here to access it. So the game. In this game, you'll play as cat or mouse. Your objective is to save Christmas by buying the star for your Christmas tree from Van Frosty. In addition to the star, you can buy as many ornaments as you can carry to decorate your tree. To gain money to buy things, you can use a computer to do online freelance programming jobs. You can also speak to Van Holly to change your name for a fee of 1 coin per character. He says that this is totally not a scam. He'll actually start calling you by your new name. He is, after all, into identity management. Is this a bug? Before the training even starts, Van Jolly approaches Mick Honeybell and says that they've been observing some weird behaviours while playing the game. They think the ghost of Christmas past is haunting it. Mick Honeybell asks them to reproduce what they saw. Van Jolly boots up the game and does the following, which you are free to replicate too. So use the computer until you get 13 coins, ask Van Holly to change your name to Scrooge Rocks! And suddenly you have 33 coins out of nowhere. Van Jolly explains that when you change your name to anything large enough, the game goes nuts. Sometimes you'll get random items in your inventory or your coins just disappear. Even the dialogues can stop working and show random gibberish. This must surely be the work of magic. But Honeybell doesn't look convinced. After some thinking, she seems to know what this is all about. Memory corruption. Remember that whenever we execute a program, this game included, all data will be processed somewhere through the computer's random access memory. In this video game, your coin count, inventory, position, movement speed, and direction are all stored somewhere in the memory, and updated as needed as the game goes on. Usually, each variable stored in memory can only be manipulated in specific ways as the developers intended. For example, you should only be able to modify your coins while working on the PC or by spending money either in the store or by changing a name. In a well-programmed game, you shouldn't be able to influence your coins in any other way. But what happens if we can indirectly change the contents of the memory space that holds the coin count? What if the game had a flaw that allows you to overwrite pieces of memory you are not supposed to? Memory corruption vulnerabilities will allow you to do that and much more. Honeybell says a debugger will be needed to check the memory contents while the game runs. Or on hearing that, Van Sprinkles says they programmed a debug panel into the game that does exactly that. This will make it easier for us. So accessing the debug panel. While they were developing this game, the Frostlings added debugging functionality to watch the memory layout of some of the game's variables. They did this because they couldn't understand why the game was suddenly crashing or behaving strangely. To access this hidden memory monitor, just press Tab in the game. You can press Tab repeatedly to cycle through 2 different views of the debugging interface. ASCII view, which the memory contents will be shown in ASCII encoding, and then Hex view, the memory contents will be shown in Hex. Viewing the contents in RAM will prove helpful for understanding how memory corruption occurs, so be sure to check the debug panel for each action you make in the game. Remember, you can always hide the debug panel by pressing Tab until it closes. Investigating the Scrooge Rocks case. Armed with the debugging panel, Mick Honeybell starts the lesson. As first step, she asks you to restart your game. Refreshing the website should work, and open the debug interface in Hex mode. Okay, so the VM should be up by now. So we go to this link, and it's loading that up. So inside here, press space to continue. We can move, press space to continue, you can move around. And press tab, and we see our debug panel. So Honeybell wants us to focus on the coins variable. Go to the computer and generate a coin. As you expected, you should see the coin count increase in the user interface and the debug panel simultaneously. We now know where the coin count is stored. So I wasn't paying attention to that. Okay, the coin is right there. Mick Honeybell then points out that right before the coin space memory, we have the playname variable. She also notes that the playname variable only has room to accommodate 12 bytes of information. But why does this matter at all? Ask a confused Van Twinkle. Because if you try to change your name to Scrooge Rocks, you would be using 13 characters, which amounts to 13 bytes, replies Mick Honeybell. Van Twinkle, still perplexed, interrupts. So what would happen with the extra byte at the end? Mick Honeybell says it will overflow to the first byte of the coin available. To prove this point, Mick Honeybell proposes replicating the same experiment, but this time we will get 13 coins and change our names to X. Well, Meanwhile, we'll keep our eyes on the debug panel. Let's try this in our game and see what happens. So we need to get 13 coins first. And with the 13 coins, we need to, I think it's it. God, was it shop? Can we go in here? Oh, is it this person we need to talk to? Okay, so person here is where we change the name. AA, BBBB, CCCC, and we'll do X. So the player name is here, and then the coins is there. So when we return, we now have 120 coins because the name filled it up. We can see 61, 61, 61. Those A, 62 B, 63 C. Then 78 must be X then in that case. And it's gone into our coins. And you can see all of a sudden we have 120 coins. The memory space of the coins variable now holds 78. Remember that 0x78 in hexadecimal equals 120 decimal. And I guess to make it clearer, switch back to here. We can see that there is an X there instead of a number. So the XL new name spilled over the coins available, and the hexadecimal is 120, or in decimal. As you can see, McCartney-Bell's predictions were correct. The game checks if the player name variable has enough space to store the new name. Instead, it keeps writing to adjacent memory, overriding the values of other variables. This vulnerability is known as a buffer overflow, and can be used to corrupt the memory right next to the vulnerability's variable. Buffer overflows occur in some programming languages, mostly C and C++, where the variable's boundaries aren't strict. If programmers don't check the boundaries themselves, it's possible to abuse a variable to read or write memory beyond the space initially reserved for it. Our game is written in C++. By now, the Frostlings are baffled. It never occurred to them that they should check the size of a variable before writing to it. Van Twinkle has another question. When the game started, the main character's name was Cat or Mouse, which only uses 10 characters. How does the game know the length of a string if no boundary checks are performed on the variable? To explain this, Honeyball asks us to do the following. Restart the game, get 3 coins, and name ourselves Elf. So we'll go here, restart the page, and we'll go in, we'll get the 3 coins we need. We'll bring up the hex memory, and we'll name ourselves Elf. So as a result, your memory layout should look at this, which it does. We need to go to ASCII version, but we can see there was a 0 there. When strings are written to memory, each character is written in order, taking 1 byte each. A null character represented in our game by a red 0 is also concatenated at the end of the string. A null character is simply a byte with value 0x00, which can be seen by changing the debug panel to hex mode. When reading a variable as a string, the game will stop at the first null character it finds. This allows programmers to store smaller strings into variables with larger capacities. Any character appearing after the null byte is ignored, even if it has a value. To explain all this, McCartney-Bell proposes a second experiment of strings. Get 16 coins and rename yourself to a name with a larger character count of 16. Okay, we've got 16, so we'll now go over to here and we will name ourselves 1234, 1234, 1234, 1234. Nice of them to not do a proper check on the text box, but anyway. So if we return this, DDDD is now going to be in our coins, and we're going to have a lot of coins. As you can see right there, we have a ton of coins now. So notice the game adds a null character after your 16 bytes, which, okay, I didn't notice that. Oh yeah, right there. There's the null byte. So to overwrite it, overwrites the shopk name variable. If you talk to shopkeeper now, you should see his name's empty. This happens when the game reads from the start of the variable up to the first null byte, which appears in the first byte in our example. Therefore, this is equivalent to having an empty string. On the other hand, if you talk to Van Holly, you should see your own name is now 16 characters long. Since C++ doesn't check variable boundaries, it reads your name from the start of the player name variable to the first null byte it finds. That's why your name is now 16 characters long, even though the player name variable should only fit 12. Part of your name now overlaps with the coin variable, so if you spend money in the shop, your visible name will also change. Buy some items and see what happens. Integers and the coin variables. Van Twinkle mistyped the name during the previous experiment, and it ended up with A, B, C, D, E, F, G. They noticed they had that number, coins, in the corner shown as the following in the debug panel. Out of curiosity, they used an online tool that converts hexadecimal to decimal numbers to check if the hexadecimal number from the debug panel matched their coin count. To their surprise, numbers were different. McCartney-Bell explains that integers in C++ are stored in a very particular way in memory. First, integers have a fixed memory space of 4 bytes, as seen in the debug panel. Secondly, an integer's bytes are stored in reverse order in most desktop machines. This is known as Little Endian byte order. Let's use an example to understand this better. If you take your current coin count of that and convert that number to hex, you'll obtain this number. corresponding to what's shown by the debug panel, but backwards. How many coins would you have if the hex value of the coins was showing in memory as follows? Input your answer at the end of the task. So when in the game, McConey is about to wrap up the lesson and call it a day, but first she explains how an attacker could now overwrite any value to the coins variable and have enough to buy the star and finish the game. On hearing this, McGreedy starts laughing maniacally and tells McConey they rigged the game so nobody could win. McConey is more than welcome to try purchase the star, McGreedy says. Confused, McConey does some quick calculations and concludes that she should be able to get enough coins. She looks at you and asks you to show how the vulnerability can be exploited. You notice that she looks a little doubtful, but still, it's up to you to win the game. Can you get a star in your inventory and prove McGreedy won? And once you get the star, interact with the Christmas tree to finish the game. So, if the coin variable had the in-memory value in the image below, how many coins would you have in the game? So we will bring up a hex to decimal converter, which we saw right there. And as I said before, it's little endian, so you go right to left. So 53, 50, 4F, 4F. So we convert it. Maybe I need to get rid of the spaces for it to convert. There we go. So we got this number. So if we put that in there, submit, and that's correct. Now we need to get a flag, which is from the shop. Let's just assume is here. And so we press the ID of the item you want to buy, followed by return. So what I think it wants us to do is enter a really large name, so it then goes all the way down to here. So that is what we will do, and it's probably going to completely break things. So let's just, actually I should probably count. So 1 2 3 4 1 2 3 4 1 2 3 4, then 1 2 3 4. So that's coins. Then shopkeeper name 1 2 3 4 1 2 3 4 1 2 3 4. Now name a name 1 2 3 4 1 2 3 4 1 2 3 4. Then that empty space 1 2 3 4. Now the items 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4. Now let's return. And if we go to here, we should probably see that. I was gonna say maybe we could see it in there, but maybe not. But surely we have the star now. You still don't have a star. Go out and talk. Okay, I think I completely misunderstood this shop. You just type it in. You have no space in inventory, press backspace to empty it. Now we do that. Hey, you're not supposed to have that kind of money. And fair and square, now give it to me. This game is supposed to be unwinnable, you know? Yeah, okay, you did. I'll give you a much cooler item for the same price. What is that? I mean, I don't want that. I want the star. Let's take a look at what. So that's a lowercase e. But what is that item? Can I just buy another one? Okay, we're going to go over here. We're going to do the same thing with the name. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. I feel like... Okay, I did get the star. So now I've got the star, which was... Oh, right, the ID of D. That should have been obvious. So we can now put the star on the tree. So here's your flag. McConey Bell is the real star. So now we go THM. So THM McConey Bell is the real star. Okay. So that is day 6 of Advent of Cyber completed. If you like this video, make sure to like and subscribe so you can watch me continue to finish this year's Advent of Cyber challenges.